Mm. Okay, so I'll get started. So apparently there are still questions for the lab 8. We can try to address those during the break. And we're back. So I'll try to finish now with the slides on the stats, and then we can start to work a little bit with the notebooks. All right. So we were looking at different visualization forms that you can use with statistical data analysis. So one of the important one for displaying frequency is the table. So we've done tables with P3 early on. Usually when you make these tables, they appear in publication alongside with other graphs that are there to present the results for statistical analysis. So this one is in the medical field. And what you see is that the table is well ordered so that you can quickly see the trends. So these are by cholesterol level. And you can see that there is the number of participants. So it's ordered by cholesterol level. There are the number of subjects that were part of the study. In the second column, the third column is the relative frequency. That is the frequency divided by the total number of counts. And then on the right side, you have the cumulative frequency that is summing up to each one of the rows. And that's typically what people tend to do. Okay, no, okay. That was strange. Okay. All right, I don't know what is happening here, but maybe I need to restart my server. But so in terms of the charts that you can do with frequency, you have some examples. Obviously, that they're all bar charts because the frequencies, they correspond to categories, and so the bar chart works well for that. If you have multiple groups, then you can use stacked or staggered bars. And you can also arrange the bar in different layouts, typically what you do with the population pyramid that is shown here on the right, because that allows you to visually compare what happens in terms of the distribution for males and female just by looking across the age values. Okay, so let me okay. I'll try to go on, but my presentation is not behaving. So the stem and leaf plot is another type of graph that is useful if you want to show distribution and a little bit the trend of the distribution, such as the density probability of estimates. And at the same time, you have the opportunity to show the data. As you can see, because it represents the distribution, you can see all the things that are related to it, such as the skewness, the modes, the tails, and the outliers. So in this one, it's actually a double stem and leaf plot, where the stem is in the middle, and the leaves are the numbers that go on the right side here and on the left. So the outliers here, probably, and you can see that this one seems to be it's hard to tell left or right here, because you need to go and look at the stem. So this one is actually skewed left. It's skewed towards the smallest values. The modes here, we can see maybe a couple of modes on the left side, and at the same time, we're basically able to read it. So we're going to see how you build these so that you can. Let me change the mask because otherwise my glasses fog. How you build those so you can understand what the values mean. All right, and if you give me a second, I'm going to restart the server, because this is doing strange things. All right. Okay. 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 This now works fine. Okay. So basically, how do you build a stem and leaf plot? Sorry, forgot to turn the phone off. You start by ordering the data, as shown is on top. So this is our data set that we see there written in the line. So it's not ordered. So the first step is to start ordering them in ascending order. Once you do that, then you select the stem and the leaf. So here we have up to 3 digits. So what we're doing is that we're encoding the tens into the stem, and then the leaf is the remaining digits. Okay. So if you have longer numbers, obviously you need to decide where you're going to cut for the stem. And then you basically list the stem on the left side. If you're just are doing one, not like the previous example, you put some separator that separates the stem from the leaf, and go and set the numbers that you see for that corresponds to the leaf on the right side. Now here you see, for example, that we don't have any number that starts with the 50s. So we basically skip it. For 60, we have 67. So we put the 7. For 70, we have 2, 3, and 8. And you see that they're all, because the data are sorted, these numbers are also sorted. Okay. The 80s, we have 3 that are 82, 84, 86, and so on. So it's important to, because you want to see the distribution, it's a little bit like an histogram. not to skip stems if you don't have data, right? Because otherwise you're kind of changing the visual appearance of the distribution, and that's not good. Now here we're going unit by unit in terms of the stem, but you can also upsize it. So and jump basically from 4 to 6. And in that case, 4 is going to have all the data for 4 and 5. 6 is going to have the data for 6 and 7, and so on. So here we can check, for instance, that 4 and 5 we just have 2. 6 and 7 we have the 7 that comes with 6 that is going to be listed first, and then we put the third here. Yeah. Okay, so that's the simple example, and it's just good to know how you build it so that you can interpret what the numbers mean. Now, when it's more complex, usually there is some annotation that tell you what was the convention that is used for the step, because otherwise you cannot know it. And we'll see in. Okay, so it's not the server, it's just doing these strange things. Okay, I need to find out what this is. Yeah, so we're going to see those in the lab. So you obviously don't do the stem and leaf by hand when it's complicated, and that is when you have a lot of data. And so, yeah, we're going to see more of those examples and what are the options so that you can form them of different sizes and for different data sets. So the one that you're most familiar with in terms of looking at the distribution is the histogram. So here we have basically bars that encode counts for each one of the bins. And what you do is that you basically take the range of the data, and you equally split it in bins of the same size, and then count the number of observations that fall within each one of the bins, and that gives you the frequency. That again, frequency is just the number of, is the count, right? So here, visually, it's important to understand the difference between the histogram and the bar chart. In a bar chart, you separate the bars because they correspond to different things. In the histogram, the bars are touching because the bins are sequential, right? Yeah, most of the time you'll see in the lab, the software is going to take some default for the bin size. And depending on your data, you may want to customize it. The reason is that depending on the bin size, your counts are going to vary, and you might remove or aggregate some of the outliers and or some of the modes. And so you need to fine tune it to find out what works. The default is usually 30 bins, and or it's computed based on some heuristic, right? But that depends on the software. So we're going to see some examples of that. So the steps to build a histogram, I think I described them already, but it's good to remind ourselves how we do. Because if you think in terms of the frequency tables that we've seen previously, that's basically an intermediate to form the histogram. Because what you do is that you create a frequency table for the bins, and the histogram is just a visualization of that, right? So the math, I guess, are obvious, so I won't go through it. And here I give you the example for what happens with different bin sizes. And you can see here that, for instance, this outlier here, you up it, and it seems that it disappears, and that part of the distribution might be just an outlier. So you have other ways to look at this distribution plot with the histogram that is using lines instead of bars, where basically you connect the tip of the bars, and then you end up with what is called a frequency polygon. So we're going also to see how you can do those in notebooks. The software is done to do that quickly. Now you can use also other forms that give you something of an histogram. One example here is here with a dot plot, where you have dots that might be instances or aggregates of your data. And that allows you to a little bit better understand how many individual counts of those you have in your histogram, as opposed to the bar that just gives you the total. Whoa. Okay, I think this is just the title. All right. Yeah, I think I've broken my slides. That's what is happening. Okay, hopefully that's not going to get worse than that. So sometimes you have to check for normality. That is because when you're doing things such as hypothesis testing, you want to look if the distribution is normal, follows a normal distribution, because some of the tests require that. So obviously you can use the histogram for that. But there are also other plots that are useful in that context that you usually you use together with a normality test. So I won't cover the normality test, but the type of plots that you would do is typically comparing your distribution with a normal distribution. And the QQ plot does that, where it does it by quantile. So here you look at the data at say 5%, 10%, and so on, and you compare that with your data distribution quantiles. And so if that follows a line, then you know that you have something that is more or less normally distributed. At least you can make that hypothesis visually, and then obviously you can go and confirm it with an appropriate test. Yeah. So now these obviously you don't do by hand. Yeah, you don't massage your data frame until you get to this point. We're going to see that you can create them directly with similar than for the histograms. You can create them with the tools in the notebooks. So the tools implement all the calculations that are needed. Yeah, so in this one, we have a smooth density estimation here that is on top of the histogram for both of them, actually. And that's the line that you see there. So that gives you an idea of how normal the distribution is or would be if you smooth it out, right? Okay. Other things that you do in data analysis is to look at correlation between the data. So that's good with heat maps. The heat maps, you can also use them when you're doing modeling, for instance, to try to present your results for different categories and see how if you're if you have a classifier, if everything that is going to be off the diagonal are going to be things that you're confusing between the different classes. So that's useful. But here we're using it for looking at correlations. You can obviously, if you have two variables, just do regression lines and also show your data so that you see how well things correlate linearly. And there are the statistical tests that are related to that. We compute persons. Here says R. Yeah. Again, the tools facilitate all of these. Okay. Okay. I don't know if we're going to be able to see this one. Yes. Okay. PCA is a technique that people are using quite a bit. It stands for principal component analysis. If you're familiar with it, the idea is to try to understand what are the main axes of the distribution of the data. And you have a couple of plots that are useful to tell you how the data fare in respect to the principal axes that come out of the PCA. So the script plot is the basic plot where you can compare the variance for each one of the components here that are the axes of the distribution that are the result of the PCA analysis. So here you would say that this component one here explains 25% of the variance of the data. The 10%, 12% is for the second component, and then you see that the others are less than 5%. The biplot is a little bit of the same, but here we try to look at the data per component, and we kind of superimpose it together with the axis. So you can see a little bit what are those main axes with respect to the data points. So here, each one of the numbers is a big point, and you see that most of the distribution seems to be between the stable width and stable length here. This is the IRIS data set. And you can also see that you have two types of two modes for the distribution. And this one is called a biplot. And that is from a paper from 1971. I think I put somewhere the reference. Yeah, I put Gabriel 71, but I didn't put the reference to the paper. I'll try to remember to add it. Some more forms. So here we're looking at hierarchical data. When you have hierarchical data, the basic plot is a graph that is in this form of a tree. So you have different layouts for this. So when you set it up in this way, then it's called dendrogram. That's the name of it. So it's just a tree representation where the subcategories are branching one of the others. And you can here you can see you can have some type of distance that is encoded into the length of the tree stems. When you go in 2D, so for just two variables, then you can use annotations such as shown here in this scatter plot to show your different clusters. But obviously this doesn't give you much of a hierarchical information. I mean, it's implicit because all the data here, this is, I think, again, the iris data set. So all the data are about the flowers. But if you have different flowers, then you can use the annotation too. So this is iris, but the iris flower. But if you have different flowers, you would have different annotation that you can color code to try to encode the hierarchy. And you could even use the color with quantitative color scale to explain the depths of the hierarchy if you have such a variable. But yeah. Okay. Okay. So a combination plot. So this is an example of a combination plot that is rather complicated because we have here the dendrograms, and then we have a heat map. But you can have combination plots that are as simple as a line chart and then a bar chart. They're also called combo plots, and we're going to see that with the tools for doing statistical graphics, that is all of these forms. It's fairly simple to add multiple layers to your graphics so that you can create some of these. Now, this one is maybe one of the more complicated ones where not all visual tools that we're going to see are going to be able to do this, because here it's more of a layout when you think about it. But for things that are simpler, such as the example I gave, a line chart and a bar chart, then it's going to be very straightforward to create those. Okay. Okay. So I have a few slides before we can move to the tools that have to do with trying to see what forms you use when you're doing modeling. So here there is a lion. So when you're trying to model, one of the things that you can do is to classify. So in this case, we would classify this picture to try to understand if there is or if there isn't a lion in there. All right. So in the case of a data set where you're trying to implement some supervised learning algorithm, what you do is that you basically have training data set, and that is labeled, and the testing data set that you're going to try to apply your model on it to see how it performs. So usually people refer to the positive samples that are of one class, and the negative samples, those that are not of the class that is of interest. So typically in our picture of the lion, so the positives are pictures where the lion is detected, and the negatives are pictures where the lion is absent. So you would split your data set based on the label. Obviously, you can do that. And then you split it based on training and test sample, where you basically try to balance the number of positives and negatives you have in your training data set. And then you reserve some samples so that you can apply your training model to it. But there are different schemes that people use to do this. I think you're familiar with all of those. And what you end up to is basically once you start testing, is this type of data where you have things that are true positive, meaning that they are actually pictures with lions and they are correctly labeled as such. Then you have false negatives. So those are pictures with lions, but they are classified as the lion being absent. And the other way around for the false positive and true negatives. And you basically go and do some statistics on these four numbers. You usually test multiple times, but you basically end up doing stats on these numbers. And so one of the things you can do to report it, I guess you're familiar with that too, but I want just to reiterate, is to build a confusion matrix. So the confusion matrix is just a table that has the counts that you can use to basically explain the results of your model performance. There are other metrics that people use, precision, recall, and there is specificity, sensitivity, and so on. So all of those you obtain when you do typical, here we're applying a classical machine learning model at random forest. And you see that as soon as we run it, we get as output the confusion matrix. So this is the table that we got before with the counts. And also a class error here. So this way you can visualize a data as shown here, together with the numbers. So here you see that they put the numbers and the color. And the reason is that they don't have legend for the colors. So it's important to put the numbers in the cells. And also because it's usually most useful for people because there is not a lot of values to see it on top of the map, so you can directly read it there as opposed to going decoding the color in a legend. Oh. Okay. Okay, let me see. Oof. Okay, so in case you have a binary classifier, then you can look at what is the compromise that you can do between setting up a threshold so that you maximize the number of false negatives or false positives, and that is really application dependent. And so what people do is that they use what is called the ROC curve, the receiver operator curve. That is here especially good. So what you want is that it maximizes the specificity, so this is as close to one as possible, and the sensitivity is there. So you have it easy to choose your threshold. Yeah. So it's just basically a line chart with the diagonal support that how people usually show it. Okay, now if you usually you end up building 20 different classifiers because you're never happy with one of them. And that is also the case if you're doing neural networks, because you might have different configurations and different parameters that you want to test. So eventually, what you want to do is look at things such as precision and recall, combined between your different classifiers / conditions. So one good way to do that is with bars, so that you can compare the performance at once. So these I just took from research papers. So this is some more examples of basically comparing conditions and classifiers. So these also are from a research paper. And here we're doing also, we're looking at the F1 score. And again, the tables that are well arranged so that people don't spend too much time in understanding which one is the best classifier, which one offers the best performance in terms of these metrics. So you see that here they're sorted by accuracy because this is the most important for this particular application. Otherwise, you can obviously sort it different ways. These, I think, are combination of classifiers, and there is different conditions that are tested. And this one is here is more to try to understand what features are the most useful for classifying. So yeah, so when we talk about features that are useful for the classifier, the theme is really to be able to interpret the results that the classifier provides, because oftentimes people don't want just the solution; they want also to understand what is it that makes the classifier useful. And for that, you want to be able to point out to some features. So here is an example of the random forest that happens to have a kind of built-in way to interpret the results with what is called the GNI measure that basically tells you for each one of the features what is their importance in the decision making. For the classifier. So here we see that this label here is most useful together with the second one, and then the other thing is to be less important. So typically, somebody who is working in this is an example from dentistry will want to understand that you know, to diagnose this. I don't know which one this is an internal derangement. These two things here are the TMJ clicking are important, and you can actually go and examine it. I think that's what the first one is saying. The TMJ is the muscle that you have here. And so if it's clicking, it means that it's not working well. And so this is the diagnosis that is associated to that. Yep. Okay, and then that's basically just a dot plot, right? All right, here we go. Yeah, I have posted the PDFs. So maybe until I fix the bug, so you may want to just look at the PDF, so you don't have to do this gymnastic of going back and forth between the slides. I think I updated it. I think I did, yeah. I'm pretty sure I updated the PDF. There are a few things that are different, but hopefully not that many. Okay. So regression models is another thing that is often used and that you want to visualize. So here is an example with a scatter plot where we're basically looking at some observations. So these are flights in Los Angeles, different waypoints for different years. And here you see that there is a smooth regression line that was created with an interval confidence of, I think this one is 95%. So what it means is that your fit is a good at a level of 5%, based on what you can see for the grid area. Again, these are in some of at least this one is kind of built-in functionality that we're going to see at least in some of the tools that are available. So you don't need to go and compute those regressions. Okay, just a few words before we finish in terms of encoding. As you have seen, you have a lot of choices. So some of the forms, they're kind of one-to-one mapping. If you want to look at the distribution, then the histogram, the smooth density estimate are good things to do. But they don't tell you always how do you encode your data, especially for the simple ones such as the scatter plots. So here you see what to do and what works best depending on the type of data. So if you have categorical data, you'll want to use either color or shape. So this one is using shape, and this one is using color. And you can see here, color at this size is superior. If you don't have a choice, then you may need to use a choice of using color. You may need to use something else here in this case than just the shapes to overcome one of the problems that is often coming around with data, and that is overflow. So here we don't know exactly how many dots we have, if there are dots on top of dots. And you see that on the right side, here the green dot, it looks like we have one, but we actually have a triangle and a dot at the same spot. So here we don't see it, but we can see it here because they're very close one to the other. So if you just use the same symbol, the same mark for both, then you don't see it. If you have continuous data, then you need something that it can be adjusted to the variable. So typically, if you're using bars, then that would be a good example. Here we see with circles, where we size the circle right to a continuous variable, and we make sure that the legend is updated so that it can be the size can be read. Right. So oftentimes you want also to be, if it's important to be precise with reading accessing the data. Then what you would do is that you would add an interactivity so that you say you can do a mouse over and actually go and read the data for that data point, because it's not always possible to put the values right in the middle of the bubbles just because of the overplotting that would happen. So you remember that in one of the plots that we saw, another option is to actually use the data, and here you would size it, but obviously if you have too much data, that becomes quickly crowded, and yeah. The symbol is superior. So using the data in the sense that you would use the text, right? So sometimes it works. Again, that depends on data. So with all these tools, the idea is that you try out things and you see what works best for the information that you want to communicate. So aside from the overplotting, there is also the question of dimension. So because we're constrained to 2 dimensions, most of the time we've seen that usually the adding a 3rd dimension makes things more complicated, especially if it's not interactive and you cannot see it from different point of view. So there one typical way to handle that is to do what is called here in different names, faceting, conditioning, latticing, questioning, and whatever. The small multiples is the name that Dusty gives it. And the idea is that you have multiple times the same type of plot for different combinations of variables. And you put this into an arranged grid so that you can compare the 2 of the variables at the same time. So here, typically, this example, this one total bill, I think this is the tip that is given. Yeah, so if a tip is given or not, made or made or something. So as you can see, it's neatly arranged, and here I think that these are histogram. So you can easily compare all the conditions 2 by 2. No, actually the tip is here. And you see that the grid is also here associated with the scatter plot. So we can see a little bit the difference in distribution when we break it down by images, right? So again, the lesson here is as soon as you have multiple dimensions, it's better to try to assemble plots, either to do it with a grid, such as here, or to separate the plot when it's not important to relate them one to another. Okay. For this is a kind of laundry list here for that I think I took from the author of ggplot2 for dealing with overplotting. So obviously you can use shapes that are transparent, so you don't have a fill, and they're also different for the different categories that you have, and that's usually the simplest that is done and what is implemented as a default in most of the tools. You can also add noise to the data, so you make sure that the data points don't fall one on top of the other. If appropriate, again, you're doing the pop plot, so here we expect that there is only one mode in these distributions. You can summarize the data in some way. Pop plot is one way to do that. The regression line is another way to do the same, that is to summarize the data. You can obviously split it so that you have less data to analyze at the same time. And so here we see an example with the small multiples that are also called 3D plots. Or the method is called faceting. Okay. And here is the same, another example of summarizing the data on a map, where the bubble represents aggregate data. Okay, so let me go back to the tools. What time is it? 2:49. Okay. Yeah. So I think I can finish this, and then we'll do a break, and then we'll do a lab in the second part. All right, so this is the table that I think I showed you early on. So the things in green are things that we've seen already. The things marked in red are what we're going to look at today and Monday. So they include chart typology type of tools for notebook, such as Matplotlib and Seaborn. Then visual analysis grammars, such as Tableau, ggplot2, the Plot9, and the Altair. I hope I say it right. Yeah, that's about it. Yeah, as you can see, it's little, but it might look a lot. So I won't go in detail on all of them, at least not during on the slides. What I'm going to do is cover some of the basics for each one of them, and then I'll go on more detail on one of them or two to tell you how they function and how they relate. Okay, so in notebooks, I will go quick on this because you know it. You use data frames. So in data frames, the idea is that you have in each one of the rows your records, and the variables are the columns here, listed in the columns. So again, these are called cases if you take statistics. Otherwise, you can call them records. In machine learning, one of the things that often happen is as soon as you have data that is nominal, such as here, this branch here, then they tend to be repeated. So here we see that we have Toyota, and so on. And so one of the concerns with this format is that you're actually repeating the data. So when you store it and or when you use it, you might use more memory than you need. So typically what happens with data frames in both R and Jupyter and all other notebooks is that they keep pointers to these. So they're not they're shown as repetition, but they're handled so that only one instance of it is instantiated, and then there is a pointer that to the memory of the location where this data is stored. So you make it efficient to deal with this type of data. Okay. Okay, this one came up nice. So what I like to do when I don't teach and do research is climb. So I have a table here of different types of stones and ways in which you can climb. And here in the middle, I have counts of areas where you can do strut climbing on granite or strut climbing on sandstone. And my question is that is this in the correct format for use with a notebook? So if you have to analyze this data, is that the way you ingest it, or what do you need to do with it? So obviously, I'm asking the question because it's not in the right format. So how do you spot that it's not in the right format, and what format would work? The format is the previous slide. That is the data frame, right? So why is it not in a data frame format? And another example of this is that we saw already is the John Hopkins data on COVID that is in the form of time series, right? So the way, okay, I was looking at it earlier, homework for next week, but the way it's structured was you have on the location, and then you have day 0 and here you have account. Right? This goes on for since the pandemic started until the last record of this, maybe weekly, without weekly. So this is why this one is not in the form of a data frame. The columns and rows, exactly. So here, in order to put it in a format for a data frame, we need to have columns here that are just variables, right? And here we need rows to have values that are associated to the variables and just observation, right? So if you want to change this one into this format, so this is what people refer to the long format. White. And so this one is the long. Right? Things go down this way. And when you do the long, then if you have strings in your variables, then you tend to repeat them, but then the data frame is going to take care of that, so that's fine. So here we would need to have a location. This day we need to call it as a day, right? And then if we are, this is say the number of infected, then we're going to have and then this number we want to put this we want to put here. Put here this number we're going to put here, right? And this location is going to be here. So we can, if we have multiple files for multiple locations, then we can just find them out. So here is the same story, right? So the variables here are the types of sports and the types of rocks, and then here is the count of locations where you can practice it. So you need to turn it in this way. I got it. I'm going to get it. Okay. Yeah. So that's really the first thing and only thing that you need to think of when you're using a notebook. And that is the same both in R and Python. Actually, the first notebooks came out of R. Okay, so now I'm going to go a little bit through the different libs, but just overview really quick. So matplotlib is a chart topology, means that you have functions that allow you to create a named plot. So this one here is the dot plot here is the name of the function that does a line chart. Okay. And then you to configure it. So the plot has certain parameters that you need to know what they are. And also to configure it, you need to know how to set things such as the axis labels, the title, and so on. And this might be plot dependent. Okay. And that is because it's a chart typology. The type of programming that is implemented by default with Matplotlib is the functional imperative programming, where you make function calls one after the other, and then you conclude by it works a little bit as a state machine. Eventually, you need to do a dot show at the end so that the plot is realized. Okay. So Seaborn, different with Matplotlib, is that he understands the data frames. So this is a Python tool, and in Python, the data frames are called pandas. The library handles the frames called pandas. And so, as you can see, you can basically directly pass in your data to the Seaborn and configure it, and then you get also the plot. As you can see, the plot is also named, so it's also a chart typology. We're just saying scatter plot. So again, each one of these, they are going to have possibly different parameters, names, and setting. Now, people build these, they try to be consistent, obviously, because otherwise you need to go and look at the documentation for every single plot. But at least you need to, if you want to do a bar chart or a scatter plot, you need to go and find out which function is necessary to use for that. And you might need to change everything inside the function call to actually realize the chart. You can use it obviously without sorry, without data frame, but that is the advantage that people are I'm sorry. I think I need to clear my throat. We need to stop here. ggplot2. Okay. ggplot2 is different from the previous one. This is a visual analysis grammar tool, and maybe we stop because it's free already, and then I'll go on with that. Okay, so I can go and clear up my throat a minute. I spoke for too long. All right, so I'll resume so that we can move on here. So ggplot2, visual analysis grammar. This is implemented in R. And we're going to play with it in RStudio. It's a visual analysis grammar in the sense that it specifies the graphic based on a grammar. So we're going to see how this works, but basically the idea is that because you want to turn these statistical graphics quickly, you have a way that is of specifying the graphic that is independent of the graphic itself, where you just specify the space of the figure and how the variables are mapped to the axis of the figure, and then specify marks that are used to render the data. And in that way, when you want to switch from a bar chart to a scatter plot, the only thing that you need to do is basically change the marks. In R, because the data frames are kind of built in, the ggplot2 works obviously naturally with that data structure. Plot9 is an implementation of the same that I think is outdated now, so I wouldn't use it, but I put it here as reference that you can use in Python notebooks. And the syntax is more or less the same, aside from the fact that you need to put some syntactic sugar to make it work for Python, but it's basically the same idea. Other people have tried to implement different variation. This one was the one that was working best. I didn't check if it's maintained, but I'm not sure it is. The go-to now is the Altair in terms of visual analysis grammar for Python. And as you can see, it's a front end that generates the Vega and Vega Lite charts that we've been playing around earlier on. And you do this with a syntax that is basically a visual analysis syntax that works more or less similar to the ggplot with some differences that I'll try to outline as we go through the notebooks and create some of the visualization forms that you can build with Altair. So the idea of the grammars came from a paper from Wilkinson in 2005. And again, the way the philosophy of it is really to go from your data to the rendered graphic with some type of structured language that allows you to manipulate the entities both from the data and from the plots that need to be set up to realize the end goal of creating the chart. So we're not going to spend too much time on the theory of it, but the basics are really that you're defining a set of components of the grammar that you then can access to set up the graphic, and these components are graphic independent. So for this original one, you see that there are things such as scales, statistics that have to do with transforming the data, there is a geometry that has to do with the type of marks that you want to use and or the geometry of the figure, the coordinates that has to do with the scaling, etc. that needs to happen for the axis, and aesthetics if you want to do color encoding, for instance, or mapping one variable to one of the axes. That's what is in there. The grammar that we're going to focus on, because we're going to use it in practice with ggplot2, is called the layered grammar of graphics. This is from 2010 from Wickham, that is the author of ggplot2. I think he did this work during his PhD and then continued to work on the software afterwards. So the basics of the grammar are depicted here in the table. You basically set up some defaults that then you can use in layers. So the defaults are for the data, typically what is your data frame that you want to use, and then the mapping. So the mappings are basically what are called aesthetic mappings in the ggplot2 and this layered grammar. And they relate to how you map the visual properties to the data. So the variables in your data frame, how do you map that to the graphic? So typically, what variables should be encoded in the x-axis, which variables should be encoded in the y-axis. If you want to encode color, that would be another aesthetic mapping. Altair uses a little bit a different word for that. They call it encoding, but it's basically the same thing. Now these are defaults, which means that you can, if you, it's up to you if you want to set them up. But if you do, then they're going to be available for the rest of the specification of the graphic that you would do through layers. If you don't, then you need to specify them in the layers that follow. That's why you have data and mapping here. Most of the time, you won't go and play around with the the positioning, but the geometries and the start are the two other things that are important. So the start is if you need to, if you want to do, for instance, an histogram, then you need to do a statistical transformation on the data, and that is encoded to the start with a specific stat name that we're going to see is called bin. That is going to automatically bin the data for you, so that when you specify some type of marks that here in the layered grammar are called geoms, then your bars will be created. So typically, for the example of the histogram, your geometries would be bars that we're going to see how to specify them. But you can also have, for scatter plot, another type of geometry that is going to be the point geometry. And the only thing that you really need to change when you swap forms is really the geometry and the mapping. So for an histogram, you don't need the x-axis because the stat takes care of it. For a scatter plot, you will need the x and y and also set up the geometry, but that's about all you need to know for creating those visual forms quickly. The rest of the system really provides you with generated automatically the coordinate systems. If you want to do setting, that is the trading flows that we've seen before. You can add this as with a functionality that is added similar a little bit to the layers. And if you want to customize the overall appearance of the graphic, there are themes that you can easily use for that. Now, I'm not going to go, I'm going to show you a couple of more slides on this. I'm not going to do the Altair, but the same ideas basically applied with different names. The main difference is really that the aesthetic mappings here are called encodings. So if you keep that in mind, I think you can understand how this thing works. So if we look in the code, how this layer grammar actually works, you see here some examples. So code-wise, you specify the default by calling this ggplot function, in which you can specify the data and mapping. The AES here is just a shortcut that allows you to say that you're specifying the mappings and to allow you to call the variables without referencing the data frame. So this MPG here is a data frame, and the highway and city variables are from the same data frame. And this defines the graphic for the default layer here for the graphic, to which we add a layer here. And because we already given all the defaults for data and mapping, if we just say that we want the geometry of points, so what we're going to get is the scatter plot, and that's what you see here. All these other ways are basically similar commands to achieve the same. You can omit here the parameter because this is a positional parameter. So the data you can omit it. And the same thing for the aesthetics, X and Y, you can omit. They need to come in that order. Here, what we're doing is just setting up the data because it's the first parameter, so we don't need to name it. But then we need to specify the mapping into the geometry, as not here, so that the geometry, the scatter plot is going to be realized. If you don't do it, then obviously the figure is going to be empty. We're going to see in the notebook that you can assign the plots to a variable. This is the operator that allows you to do this in R. And then you can write the same in 2 lines, where you can say my defaults here, I will add this point, and then you can show it here. Now, this is useful when you want to add multiple layers to do combo plots, and then you can just pile up the lines that do E plus geometry or whatever you would like to realize. Okay. This I'll skip, but that's basically what I explained with the AES that allows you to reference the variables in the data frame, and some more sugar syntax here that you can use if you want to transform the data in this way. But again, you can also do it directly on the data frame. Yeah, so this is here more of the same. So you have other aesthetic mappings that X and Y that you use. For instance, if you want to map the color to another variable, then you will need to name it. I don't like this. The color is positional. Not sure. But what you can do is for all the named variables that are words, is either use the shorthand or use from here, and you can get the same result with that. This last example here is bad because it's bad because we're not setting the AES. So we're setting the variables without calling the AES function. And then basically the software doesn't know what this variable is referring to in terms of which data frame it is coming from, right? So you always need to remember to set the AES, both in the default and in the geometry if you want to specify it. So this is adding layers. So I think I've already explained that. So here we're adding a regression line, a smooth regression line, and you see that it's as simple as saying plus geon smooth. So that's the geometry that is going to realize the regression and put the regression line with the interval confidence that you can see there. So it's very quick to do. There are a number of name slots that you can use through the geometries, and we're going to see all of those in the lab. Just a few words about how you can specify faceting. So this is the model formula. Y is modeled by X. Sorry, Y model X. And you can use it in the faceting formulas to refer to the columns and rows, where the Y are the rows and the X are the columns. You can see here. Right? So the columns here are the X part of the formula, and the rows are the Y part of the formula. Okay. So this used to be the older way of specifying the layout for the faceting. The newer way is with columns and rows. But you will see older code with the model formula. So I didn't want you to get confused. So depending on how you set up the faceting here, we're playing around with the grid. So there are two ways to faceting. There is the facet grid and the facet graph. Here you see that if you set up by column, then this is the layout that you're going to do it. If you do it by rows, then this is what you get. These are positional, so if you do both columns and rows, then you get a grid. Okay. The facet graph just graphs things around in order, left to right, and then goes to the new line. And it works basically the same, but you only need to specify one variable. So all the notation there is a little bit awkward, but that's what it is. So these are some renderings of themes. So they do have a theme that is minimalistic that you can use, and the way to use the theme is fairly simple. You just need to import the DG themes library, and then you just set up you call the theme on your graphic, and you're basically done. There is a black and white that is that I don't show there, but is the first one. Yeah. This one is black and white from the name, but here I'm saying that I want colors, so obviously it's giving me colors. Okay, and this is a little bit of a complex example, but we're going to play with this in the yeah in the R notebook. But my point here is that you see that I basically wrote this and then click in one line on screen, and I get two encoding both for size and for color for a scatter plot, which is quite neat. And then that's basically the power of using a layer grammar as opposed to if you need to do this with chart typography, is going to be, unless you have a function that does just this one, is going to be more complicated. Now, if you take the previous example and you look at Tableau, so Tableau is basically the same idea, but instead of doing it by code, you're using a visual grammar visually by setting up here the variables to the x and y of the figure, and then doing the encodings here. Right, and I've put a slide here that, oh, this one stayed on. That's a miracle. That shows you how the ggplot grammar maps to the ggplot2 grammar. So what is good with this grammar is that once you learn how to use the grammar, then it's very quick to prototype plots, very different types of plots, and that's what you want to do, right, in statistical analysis. Let me see if we can. Yeah, we have 10 minutes to get started with the lab, so I'll go and do that. Oops, I just want to. No. Okay, I'm going to share the screen here. Okay, here we go. Okay, so I don't know if I can make this bigger. Okay, so this is basically what you have, the A9 starter. If you have not done so, you probably want to go and let me get back here and install the software for R, because otherwise you can't follow through. Lab 9. Okay. So yeah, for R Studio, you really want to make sure that you install R first. Then you can install R Studio just by going to the link and clicking install. It should work in Mac and Windows. For Jupyter notebook, I prefer that you use the Jupyter Lab. But if you don't want to install things or this for the lab, Colab would work too. But yeah, so I think that yeah, I'm not sure how easy it is to get the repository to work with Colab. If you can get it to work so that you can submit your work, then fine with me. For submitting the R part, you do need the R Studio. So if you have problem with that, again, post in the Slack and we can try to help. So the layout here is a little bit different from the usual. So you get the assignment and the README that are still there. And then you have here two. So this is our notebook. And here is our project that we're going to open in a minute. And this is a Python, a Jupyter notebook, or at least the stub of it. So these two you will want to use for the assignment that is here. And everything that has to do with the lab is still under the lab. So if you look at the README, okay, I'm going to use this to open our studio, or you can start our studio and then load this file by opening it as a project. And it also tells you how to do how to deal with Jupyter, but we can do this when we get there. Okay, I'm not sure if this is the default or I'm using a dark theme or something. But this is basically our studio. That is a front end to run our code. There is an online version too. I don't think you can use it for doing the lab. But if you figure out a way and you really don't want to install it, yeah, let me know. I'm open to it. Yeah, as long as you can do the lab. So the R notebooks here are marked with the red little symbol. They're the RMD files, which are basically our markdown files that we're going to open in a minute, and that you can see here listed under files. There is also a Git integration here that you can get on the top, and we'll see how this windows come into play. The rest of the files here are the Python notebooks that you could run in here, but we're going to do it in Jupyter Lab. It's going to be easier. Some of the data are in here, so you can go and look at them. I think that you can, yeah, you can view them. You can view them as file, or you can import them as dataset, which I don't know what happens. Okay, he wants to install packages. So this is a good occasion to see how RStudio works. So as you see, R is using a repository of packages, and RStudio is smart enough when you try to ask for some functionality to find out that you need some extra packages. So here this is a CSV file, so I guess we're going to see in a minute what we're going to do, or hopefully something useful. But it's basically getting packages that have to do with opening CSV files. So hopefully we can maybe see this data in a tabular form. And if it's going to take too long, I'm not going to wait. Let's see. Okay, we're almost there. Okay, yeah. So here you see that you get a preview of the data that's kind of fancy, where you can probably go and sort it by variable and filter the data and do all kinds of operations. And yeah, and it even gives you the code that you can use in a notebook to preview this. And okay, ultimately the idea is that you can, whatever you filter here, you can import. So we're not going to do that, but that was a good learning opportunity, at least for me. So we're going to start with this R notebooks. So there are essentially three. I think we have the time to at least do the first one. So to open it, you just click it. It's similar to the Jupyter notebooks if you're familiar with those. What you see here is the markdown part of it. And then these are the code blocks that you can execute by clicking the green arrow. And you can also execute parts of the notebook and of the code blocks are called chunks through this menu. So if you want to clear everything then and restart the R interpreter, you can go there. If you want to run everything, which I'm going to do now, you can just go here. And then it should, as you can see, just execute everything that is in the notebook. So R comes with some data sets. And also packages of data sets similar to what we have in Python. So here we're asking for the ggplot2 package because one of these cells is asking for that. So for the ELK is similar to what you have in Python. In Jupyter, where you put the question mark with the function name, and then it's going to tell you how this works. So I'm going to redo this one, and you get the ELK file nicely integrated here on the side with examples usually at the bottom, and those are always welcome to, in case you don't understand how things work. If you need to print something, you do it with paste, and so you see that you can separate things with the semicolon. Whenever you have an output, it's displayed right under the cell, under the chunk. Sorry, I should say. You can do the usual operations with that you would do in a regular notebook with any other interpreter. The only thing here is to realize that the assignment operator you must never use, the equal, and that is because the assignment operator here in R is this left arrow. Okay, so just use that, and you'll be safe. Now here we're assigning X to this simple operations here. And what is printing out is the result of the, yeah, I don't know, actually. Let's try. Yeah, no, it doesn't print. So if you just do the assignment, obviously, I mean, not obviously, but it doesn't print anything. What is printed is here the first line of the operation, right? If you want to print the actual variable, you need to set it on a line by itself. And that's what you see here. So this is how you create functions. You probably don't need to worry about this, but just in case you want to reuse some code that you find left or right. In terms of data types, you mostly have strings. Again, single quote, double quote is the same story. The integer, floats, booleans are listed here. You see that the bools are capitals, true and false. So you want to be careful with that. Again, is duck typing, so similar to JavaScript and Python. The type is inferred, or you can force it if you need to, and we're going to see how to do that. If you need to create a vector, this is the syntax. So this is a column vector and it's the C in front. And then you can see that the vectors, you can throw pretty much anything you like inside, and they will take it. And to access, the big difference is that we always in our work with indexes that starts at 1, as opposed to 0 in Python and JavaScript. So packages, you see this one. So I'm just going to show you So here, for me, it's working. No, sorry. This line here is the line that loads the package, but this line is the line that actually imports the package, downloads the package, and imports it into the ID from a central repository that you don't need to worry too much about. So this is one way to do it with the command line. I put it here so that you don't need to go and do it in the other way, at least for this one. But if I want to find more packages, you can go here on the side where you have packages. And here you have a list of all of those that are available in base R. That is those that come with the R package. And you see that here with the one that we've loaded, that is the ggplot2, is marked with a check mark. Now, if you want to install a package, say I'm going to install here ggplot2, then you would go here and type the name of the package. And it's there, so it helps you with the completion, and then you just type install, and that's the other way to do it with the IDE. Okay. Yeah, I think I'll stop here. Yeah, let me get to the data frame. So if you want, you can at least continue a little bit on your own, and otherwise we resume on Monday. So loading CSV files, you have the read CSV function that is here. So here, this is a data set that is in the data as I shown you earlier. You can use head and tail, obviously, df to get a printout, and you can see that it appears right here under. Now the data frame is created by data.frame. So here we're creating a simple data frame that, right here with some sample data. So this is one way, but obviously you can also just load data from a CSV file into a data frame, and we're going to see how to do that. Now the repeated strings, you need to tell the data frame that you want those to be used as categories, and you can have order or unordered categories, and those are called factors in R. Okay, so here we're creating a list of factors to use for a data frame, and if you look at the factors, it will explain you those differences between the ordered and unordered. So this is another example where we create a data frame from a vector. So we create the vector and just put it into the data frame. This is another example, again, where we create a data frame with vector of different types. Calling the head, tails, the column names. So you see that when you do multiple operations here, they appear in different frames. So you can go and look at the output. Yeah, these are ways to access the data in the data frame. You can use the short notation with the $, and otherwise you can use the numbers that are indexed starting at 0, right? This is the slicing operation. It's similar to what you have in Python. You probably don't need it. And this is what I wanted to show you. That is how you load a data frame with the red CSV that basically gives you what you expect. That is the data frame. And the summary function gives you the descriptive statistic for all the variables that you have here. Right? If I want to just write the data frame, here it is, right? So you see that it's a proper data frame. Okay. So with this said, I think that you can, if you want, you can start doing maybe this one and the next one, and then we'll work the rest on Monday. Okay. Thank you.